So today we are going to talk about aggregation and filtering. So previously we've talked about three strategies to handle complexity. One was that you derive new data to show within a view. Then was manipulating, right? Changing a view over time. Um, and then we talked about faceting across multiple views and some of the strategies for that. So today we're going to talk about the fourth major strategy, and that is reducing the amount of data shown within a single view. So that includes filtering, aggregation, embedding. So just to put that into perspective, remember we had our bigger picture of all of the idioms to both encode and interact with data. And so reducing fits into that last category. Now, so let's talk about reducing items and attributes. That can be filtering. You can filter either items or attributes. It can be aggregating, again, either items or attributes. Now, when I say reducing the amount of stuff visible in a view, what I usually actually mean is either way. We could either talk about reducing or we could talk about increasing the amount of information shown. So we're typically thinking about this often, not always, but often in a dynamic or interactive context where we're choosing on the fly how to see that. So with filtering, the good thing about that is it's straightforward and it's intuitive. The idea is by filtering, I simply mean you don't show certain things. Um, and so you can filter items, you can filter attributes. So it's nice because it's easy to explain to people. It's easy to compute on a machine. In fact, typically filtering reduces the computational load. Um, so what's the problem with it? Why don't we just declare victory with that? Well, there's this phrase out of sight, out of mind, and it really reflects the reality of how people think about things. So once you've filtered something out, even if you yourself filtered it out 30 seconds ago, within a few minutes, you might start systematically not thinking about the items that you filtered out. It's very hard to keep those at the front of mind when you don't see them. So while filtering is effective in some ways, you really do lose information. So, think of it as compression in the classic information theoretic sense. Um, you've lost information. Now, aggregation in context is where you are still not drawing every single thing, but you've got some sort of proxy that stands in for the set of things that you're not showing. So there's this proxy element. And again, that can work for either items or attributes, and we'll talk at length about both of those. So what's nice is that you actually do have some sort of signal, some sort of information about that whole set of things that you're not showing. Now, the devil is in the details. What's hard about aggregation is how do you aggregate in a way that you actually provide the right useful signal or information about what you're not showing. So it's tricky. You can think about it as a visualization complete problem where to figure out how to kind of correctly aggregate really is a microcosm of all of the challenges of visualization at all. Um, so we'll talk through some of these ideas in more detail as we go. And I just want to emphasize that remember, these are not mutually exclusive. It's extremely common that you do both filtering and aggregation. In fact, thinking about the major ways to handle complexity, we typically do use a combination of all of those. So, right, you can combine reducing and interaction and faceting across multiple views and deriving new data. So all of these are combinable. These are all separable and combinable choices. So with filtering, all right, the basic idea is straightforward. We're just eliminating some things. It could be items, it could be attributes. And so, what do we eliminate? How do we decide? The idea is that we eliminate according to any possible way you can think of to partition a data set into two sets, the thing you keep and the thing you toss. And so, for example, you could filter according to some specific threshold on an attribute value. You could say, well, any item whose for this particular attribute, if it's less than some value, I'm going to filter it out or keep it. So, right, what you're typically trying to do is, keep the things you care about and get rid of the things that you don't care about at any given, say, moment during an interactive visualization session. Now, sometimes you can think about the word query. Those of you who are um, up on databases might think, well, what's the relationship between filtering and queries? And they're sort of inverses of each other. Typically, if you're thinking about a query, you'd start with nothing and you would add in elements that match the query. And with filtering, you start with everything and you remove elements that, match something you can think of as very much like a query. So whether you want to start with nothing and add or start with everything and remove, it really depends on what you're doing. Often with data sets that are enormous, like you might think of, a database that's too big to even fit into computer main memory, then maybe it's safer to start with the query point of view. If you're in an interactive visualization context where, for example, you might already be able to do some sort of overview of drawing everything, maybe it's an aggregate overview, as we'll talk about. But if you've already got all the items in main memory, then it might be completely feasible to start with that and then remove things from that. So here's an example, just to give you something concrete. This is an older system called Film Finder, but it does a nice job of really sort of being an example of the kind of things you can do. So here we've got a dynamic scatter plot. So it's interactive. Um, and so along the bottom row, we have the year that a movie was made. Along the vertical axis, we've got the popularity. It's color coded by genre. And when we see the sort of full data set on the left here, well, we see obviously we can notice more movies got made over time. There's a mix of genres. But in fact, it's too crowded to even begin to say put labels on all of them. There just wouldn't be enough room. There'd be a lot of overplotting. So in this case, what they're doing is they've now, with all these sliders here in the control panel, now let's actually pick a few things. We've filtered for length, so we don't have the really short ones or the really long ones. And they've filtered by actor. So this is a sort of alphabetical slider. With this alpha slider, we picked Sean Connery, and now we see only a very small subset of those movies. There's enough time that we can do a reasonably good job with a naive algorithm for drawing labels, or we just simply draw them all. A little bit of occlusion, but not too bad. So the thing to notice is that this particular approach of dynamic queries, sometimes they're called dynamic queries, sometimes they're just called interactive filtering, is this tight coupling where as you move the sliders, you immediately see things update. And this is one of the nice things about interactive filtering in a visualization context, is you can see what happens. You have a very clear sense of what happens as you go. You don't have to worry. Sometimes, for example, if you're doing a query with the database, you might either get way too many hits or 0 hits, and it might be hard to know how to actually incrementally refine to get what you want. Whereas with this kind of tightly coupled interactive filtering, it can be very straightforward to understand this. Let's look at another example. So here is thinking about filtering explicitly in the context of multiple views. So this is the cross-filter system, also created by Mike Bostock, the person who was the chief designer of D3. And this is an approach for filtering items, just like we saw. And so this is really coordinating both a view and a control, as we'll talk about in just a few slides with histograms. What we have are a number of histograms that are all tightly linked together. That's the cross part of cross filtering. And when any of these ranges change, then all of these update. So let's actually take a look and see an example of that. So here's actually quite a large data set. I believe we can see 200,000 flights. Um, and what you want to notice is there's very quick update. In fact, the cross-filter package is actually mostly for data management under the hood. Let's take a look at, notice how as I update these, so what I'm doing is I'm filtering, um, and let's take a look at the very delayed flights over here. And notice how when I update one of these, and you can think of these as a multiple view system, where we have time of day, the amount of delay, the distance the flight was, and when these things happen. So I can move these filter ranges in one view and see how the other views update. Now, what I want you to notice, remember that we've talked about layering before. So we have this layering where we basically have a foreground layer, which is blue, and a background layer, which is gray, so that we're able to see not only what has been filtered, the filtered out parts are not completely invisible, they're grayed out. And so this is an important way to try to mitigate one of the big problems of filtering, which is if you simply have things vanish, it's hard to reason about them. So one thing you can do is use filtering to really create a foreground versus a background layer. And that is a extremely useful strategy. Now you notice how it doesn't completely deal with things like visual clutter. There's still situations where you really would want to filter out things and then simply not draw them. But this is a case where it's useful to be able to filter things and then see them as a foreground layer as opposed to a background layer. For those of you who are interested in possibly using something like this for your final projects, um, be aware, although this package is not actually maintained anymore, there is certainly still some active development with variants of this, and it really does give you some infrastructure for doing this kind of interaction very quickly, even as the data set is large. Okay. So let's look at another example of this. Um, and it's a bit more sort of tied to a story, another one of these data journalism examples from the New York Times. Um, so with this one, this is about renting and buying, always interesting in a Vancouver real estate context. So notice how what's happening here is as we are changing one of these, and let's actually, we're seeing that as we move things along the slider, we're seeing a lot of interaction where actually this curve is changing about when it makes sense to rent versus to buy. Um, and the thing I wanted to note is as we move one of these, notice how, well, actually, we're not seeing too much change here. Okay, here's where we can see a fair amount of change. So notice how one of these views is driving these others. So this really is interacting between these cross-filtered views. So one of these controls affects all the others. Okay, so that's been a pretty quick overview of filtering in many ways, because filtering is the easiest thing to think about. And the much more complex thing to think about is aggregation. So, and of course, we'll see some interesting combinations of both. Now, when we're aggregating, so to define that precisely, we're saying that some group of elements is going to be represented by a smaller number of derived elements. And again, we can think about this for either items or attributes. So let's look at some examples. Now, with a histogram, what we're seeing is obviously, I think everyone is familiar with the histogram, but again, let's do this decomposing and analysis in terms of a visualization framework. What's going on here is it is a static, not a dynamic, but a static approach to aggregating items. Now, of course, we are able to make this dynamic. In fact, we just saw a few examples of using histograms dynamically. But the sort of base idiom is static item aggregation. And so here we're seeing an example of, for example, how many cats way different amounts. We see a pretty normal distribution. So not surprisingly, histograms are very well tuned for the task of finding a distribution. So remember back to that set of abstract tasks, understanding distributions of a single attribute, that is really what histograms are incredibly good at. Um, but let's think about what's happening under the hood. How is it that we make this thing that sort of looks like a bar chart, only it's not exactly a bar chart of the base data? What are we doing? Well, we take some basic table of data and we derive a new table. This new derived table, the keys of that table are the bins of the histograms. And the values in this table are the counts, the number of items in the original table that fall into that bin. And so it's actually helpful to think of histograms in terms of deriving data, where the derived data are these counts. Now, in terms of people's ability to reason about histograms, well, the size of the bins is crucial. How many bins do you chop this up into? Should this be, 2 bins or 5 or 6 bins or 20 bins or 100 bins? And the number of bins, that is the discretization, can very much affect what kind of visual pattern you see. And so this is a sort of classic problem with histograms, is how many bins. You'll notice there's going to be many classic problems of, anytime you have to pick K of something, how do you pick K? How do you pick that number? One answer could be you don't necessarily know a priori, and this is an opportunity for interaction. You could allow the users to control the bin size on the fly so that they can just quickly and easily inspect for any given data set what's happening with that. All right, so let's actually look at an example for a few reasons. One, to actually understand how histograms work, and also it's a really nice example of scrollytelling. Remember, scrollytelling was having a sort of linear ordering of items so that as you progressed through, you see story, you're able to sort of linearly progress through a story. Do remember that that's one possibility that you might want for interactions for your final projects. So wait, that is not what I wanted. I wanted to go backwards and click on this. Let's see that. I see, that was not an interactive link. Let's just do that the hard way. And this is a nice explainer by Aaron Lunzer and Amelia McNamara that encourage you, and what I will actually encourage you to do is to click through this and investigate it yourself. We're not going to take the time to do that in this lecture, but there's some really nice material here. And so notice how there is the use of animated transitions in this one, of gathering data items, sorting them into a list, drawing a number line, placing the items onto the number line. It's a nice little animation of having them fall down. And of course, we can still do this even if there's a lot more items. And then this idea of portioning them into bins. And now thinking about where to break between the bins. You can vary things like, varying the offset, varying the number of bins. We're not going to go into the details of how to calculate this right now. But notice how this is an example of playing around with what some obvious offsets might be, playing around with, let's turn off those offsets for the moment, playing around with the width. So here we have, and so remember how I was saying that the number of bins can really affect the patterns you see. And this is an interactive example of that. For those of you who've got any sort of a background in signal processing, you can think of whether you want a low pass filter or a high pass filter, right? That is, do you want to see large scale patterns or maybe some smaller scale patterns? Do you consider those small scale patterns useful and interesting information, or is it just noise? So this is a nice example of playing around interactively with histograms. Okay, so I'll let you play around with that more. if you like on your own time, and I do recommend that. So of course, there are various algorithmic approaches to attempting to predict the right number of bins. These are all sort of have strengths and weaknesses. None of them are ideal. And that's why interactivity can just be a really nice solution that allows you to quickly tailor it for the characteristics of a particular data set. There are a few rules of thumb, like if you have n items, then the square root of n or log 2 of n plus 1 are both a few relatively common rules of thumb. So now let's think about what can you do with histograms. An interesting thing is this idea of scented widgets. So you might think, what is that name all about? The idea is that we're going to take some widget, like in this case a slider, and we're going to augment it to show this idea of information scent. And that is a cute term that comes out of information foraging theory that was actually originally developed at the Research Lab Xerox PARC, with this idea of information foraging, just like animals are looking for food and they try to figure out where is there more likely to be, berries in the bushes by some sort of scent. The idea of information scent is there likely to be useful information in a particular place? Is it worth looking further here, or should you move on to some other area of the information space in an analogy to, the physical space an animal would forage for food in. And so you're trying to show, should, what, instead of just making people move a slider back and forth and seeing how some interactive display responds to that, what if you could communicate in advance what the distribution was? Because remember, histograms are very, very good for showing distributions of single attributes. So any kind of a slider that allows you to control attribute values is a natural place to put a mini little histogram. And you can think of this as a really concise use of space. By having a slider, you might have thought of the slider as a control, not a display, but a control. You often have, controls on one pane and then a big interactive display on the other. But this actually blurs that boundary and allows you to think about having display and controls sort of integrated together using space really concisely. So the idea of scented widgets in theory is quite broad, but where they really caught on is this use of histograms over sliders. So here, for example, is a display. There's a lot going on that's complex with networks that I'm not going to get into right now. But what I want you to notice is this part here where there are these really, really concise sliders. This is a very small number of pixels that we're using to say, here's say age, betweenness, closeness. These are a bunch of attributes. And one thing you'll immediately notice from these, and these are actually bi-sliders, that is, there's two controls, a min and a max. So you're not just picking a single value, you're able to pick a range through these histograms. We can immediately see, right, there's a few that look like normal distributions like age and income, latitude and longitude. These Nito X and Nito Ys are actually just the specific spot where they are laid out in the network. And then, we see some that seem to be these more sort of power law distributions that start out heavy and then have long tails, like crime, betweenness. There's some bimodal things. Notice how closeness, there's a few really close and a few really far. State, that looks like it's probably a categorical variable where we're not really seeing something that's varying quantitatively, but we're just able to pick different values. So, and we see that with both state and county, that seems reasonable. So what I want you to notice is how few pixels of the display was used. This is a very information dense visualization idiom or instantiation of an idiom. So very, very dense, and we're able to see a lot with a small number of pixels because we've taken something that could have just been a slider and we've augmented it with these little histograms. Let's look at another example. This one is not quite as visually concise. This is actually showing, this is an interesting interface for looking at large image collections. And I'm not going to get into the details of the entire interface, but I want you to notice here are, again, some sliders for things like the camera model, the date the picture was taken, the location. And again, we've got by sliders and we've got these histograms on top of each slider. We're taking more screen real estate for this, but we're also getting more. We don't just have these very thin 1 pixel wide lines. Notice how we've got something where as we change the range on some sliders, for example, here we've picked just these 2 models out of the total of 4. Now we're able to see highlighted in these other histogram bars, these subsets. And so we're able to actually see this progression that there were originally 92,000 images, and based on this filtering, we're now seeing that there's only 23,000 once we're filtering by country. And then once we filter by date and time, we're only seeing 11,000. So this way of indicating within the histogram bar what the selected values are based on the filters. So we're really able to see that how, on a per bar basis, we're able to see, in this case, for the bright green selections, they're roughly equal, but for the darker green, one is much more than the other. So we're able to see whether there is a sort of, roughly proportionate amount or whether there's some disproportionate amounts selected in all of these. So scented histogram sliders, certainly something you might want to think about for your own projects if you have a situation where you need to look at distributions of attribute values and control attribute values with any kind of a filter or selector. This could be an interesting thing for you to try. Here's another example with the Kashif system. This is one that's very much based on interactive filtering. And it's also got heavy use of these scented widgets of sort of going in between controls and displays. And let's actually take a look at this one. This is looking at the Olympics gallery. Let's get this loaded up here. Come on, you can do it. Load. Well, while we're waiting for that to load, which does not seem to be the speediest of loads at the moment. So what they're doing here is they are, notice how this is definitely a multiple view system. It's multi-form views in the sense that we have a lot of different ones. And like a lot of multi-view systems, it then allows you to look, to focus on different attributes and do things like order according to the attribute to easily find per attribute things. You can either look by geographic location like country, you can look by sport, you can filter by metals. Let's see, today is not the day for Kashif. Perhaps we will move on. So feel free to play around with that afterwards on your own. But it's another example of the use of scented widgets, because notice how we have these histograms above the sliders to get some sense of what that attribute's going to look like. Another example of this, sort of same mentality with interactive legends, again, is sort of blurring the boundaries between what is a control and what is a display. So here's an example where instead of just having a completely static legend, this is actually a paper from Nathalie Henry Riche, we've got controls that really combine that sort of static with something dynamic. And so notice how these are sort of acting as little sliders that allow you to interact with what might look more like a legend. So the upper and lower bound of what's being filtered is actually visible on these. Here's something that's size-coded circles that is both the legend and also the control. So an interesting thing for you to think about for your own projects, especially if you're thinking about how to do your unique, innovative view. You can imagine designing something interesting along these lines. Okay, so we've talked through histograms quite a bit. Let's talk through another thing you've probably seen before, a box plot, and think about that from an analysis point of view. So box plot is another example of static rather than dynamic. Of course, you could make them interactive, but the core of a box plot is something that's static, and it's aggregating. And again, we're aggregating items. And these are also exactly tuned for that same task of finding a distribution. But they're even more visually concise in terms of the number of pixels than a histogram. With a histogram, you would need a relatively large display area to show that histogram. And with a box plot, what we're doing is just like with the histogram, we are also deriving data. But what we're deriving, and so our input data is, a tabular data where we've got one attribute, or of course we could do multiple if we're trying to do something like this with a multiple box plot chart, as we see here on the right. But we're deriving is not a set of bins. We're actually deriving just 5 quantitative attributes: a median, lower and upper quartiles, and lower and upper fences. So these are carefully chosen statistical, aggregation values. And then these are mapped into a glyph, a visual representation where we've got a central line, we've got a box that has the upper and lower section. Sometimes box plots are called box and whisker plots, where you can call these the whiskers or the fences. And then anything that's beyond these chosen values that are the fences are actually explicitly shown as outliers in some variants of the box plot. And so notice how it doesn't matter whether you had 100 items or 1,000,000 items, you need the same number of pixels to show a box plot. And that's a property that both box plots and histograms have, is they allow you to aggregate essentially an unlimited number of items into a finite set of pixels because you are explicitly doing computations to show those distributions. Now, just like there have been many variations of histograms, box plots have been extensively explored. So what are they good for and what are they not as good for? So these so-called interquartile ranges, right? This is carefully designed to try to really capture certain aspects of normal distributions. So box plots are really, really good if you've got a normal distribution. They really capture the important aspects of normal, the family of distributions that are close to normal. Like, where is the median? Roughly how wide or skinny is that bell curve? But they're not as good for multimodal, bimodal or multimodal distributions. What if there's more than one peak? Does the box plot really capture what's going on? And the short answer is no, it does not. So here is a nice example. These are 4 different distributions, and they all are represented by the same box plot. So we have a sort of a normal distribution that really works well. Notice how this bimodal distribution, we can't see that it's bimodal from the box plot. We can't really see that, examples where there's a sharp peak or it's very skewed. This box plot doesn't show us those specific aspects of the data. And now we're getting back to something we talked about on the very first day of class, where we looked at things like Anscombe's quartet, and we noted that static statistical summaries often hide crucial information. They work well in contexts where you understand that you're capturing what matters if you're modeling something. So box plot is good if the model of your data is that it's a normal distribution, but it's not so good if that's not what's happening in your data set. Often visualization is used exactly when you want to check whether your assumptions are correct. Does the data have a normal distribution, or is it something else? Or do you have no idea what the distribution is, so you don't want to make any assumptions? So this is a situation where you often want to actually go in and check and see the data, maybe interact with it. So here's some examples of variants of box plots that actually are able to capture more structure of the data set. One of these variants, what's called a violin plot, is where you're really sort of combining, mashing up a basic box plot with some idea of a density function, a probability density function trying to show what's actually happening in more detail. So if you just have normal distributions, well then violin plots and box plots, seem quite similar to each other, just with somewhat different shapes. But once you start having some interesting multimodal distributions, as we see down here, then even though all those box plots are the same, we actually start to see that structure much more with these violin plots, where the width of the plot is actually capturing the amount of data that is appearing in the attribute value there. And of course, what I do want you to notice with all of these is that these are very information dense representations as well. With a relatively small number of pixels, you're capturing a complete distribution of an attribute in a way that's independent of the number of items that you're dealing with. So these are all for, each one of these plots is for a single attribute. But they're concise enough that you could actually either, you could look at many attributes at once, or attributes for, many different categorical data sets at once, as we're seeing here, right? We're easily able to look at 6 or 7 of these. So this is 6 or 7 attributes that we are taking a look at. And that actually brings us to the idea of density plots. So we certainly don't just have to think about them in the context of box plots. So density plots, they have a lot of different names. Sometimes they're called kernel density plots, or kernel density estimation, KDE is another acronym you'll see. And so actually these are very close to what you would get from a histogram. You can think of them as a smoothed, continuous version of a histogram, where you're directly estimating them from some particular data set. Again, for those who have had a signal processing background, the way you can think about these is that you have some sort of continuous curve that you're drawing at each data point. You can think of this as a kernel. Often you just use a Gaussian bell curve. And then you're really just adding all these curves together, again, with a sort of signal processing point of view. And depending on how wide that curve is, you can, the width of that can give you different amounts of smoothing with this density plot. So we're not going to go deep into that in this class. It's a bit beyond the scope of what we're going to focus on, but for those who are interested, there's certainly a lot more resources. Again, this could be an interesting territory for one of your final project plots. But let's just take a quick look at an example. There is some implementations, so there's some blocks out there already in D3. And let's just take a quick look at how this one is. What we want to play around with is, as we change the bandwidth, we're going to see, either a much smoother representation, or a much more allowing the high frequency data through interpretation of, in this case, we're looking at Old Faithful data. And this is an idea that works not only in one dimension, as in basically a smoothed histogram. You can also do the same thing in 2 dimensions if you want to have, here we're looking at a scatter plot. So you can think of this as a sort of something that you can do on top of a scatter plot, rather than in 2D, rather than just a histogram in 1D. And then we are actually able to see these density contours. So that, for those of you who remember the isocontours that we talked about with topographic maps with spatial data, this is related to that idea. Okay, but let's get back to our main point for today. This idea that there's some ways that we can take some of these basic statistical graphics that we've already heard about and do something interesting with them as the scale of the data increases. So just the way we can think of density plots as sort of variations, we can think, well, what would it look like if we actually had a scatter plot and we wanted to think of that as something continuous? So the thing to think about is what's tricky about scatter plots is overplotting, right? If you've got too many points in a scatter plot, well, sometimes you'll have a whole lot of points on top of each other. And then you can't really tell, is that 1 point? Is that 5 points? Is that 20 points? Is it 1,000 points? Um, and so continuous scatter plots are one idea of how you can try to take this idea and explicitly show that to the viewer. So the way you think about a continuous scatter plot is, again, we're going to do something with derived data. And this is a static way to aggregate items. So, and our derived data is that we actually think about the scatter plot itself as something that we could monitor. So we're going to think of a scatter plot as being broken up into pixels, and each one of those pixels, each one of those XY locations in the image, the scatter plot image, we're going to just count how much overplotting is there on that pixel. So of course, if you had a very sparse scatter plot, this wouldn't be very interesting. But as you get really dense scatter plots, as we're seeing here, then what we can do is keep track of the amount of overplotting, and then actually color code the overplotting so that we can see, instead of just a big, black mass that we would see if this were just a bunch of black points on a white background, we're actually able to see that there's a lot of internal structure based on just the amount of overplotting. So this really is an approach to scale up something like a scatter plot where, before I said, well, maybe you could get, hundreds of items, maybe around 1,000 or so before you really run out of the ability to distinguish. Now you could see, tens of thousands, hundreds of thousands, even millions of items because you are explicitly encoding the overplotting using color. Now, thinking of color, notice how, we just heard about color last time. What have we got here? Well, it's a sequential uh, color map so we've got changes of hue, but we also have changes of luminance. It's one of these monotonically increasing luminance as we change hues, carefully designed color maps. So the key point I want you to think about is, as you're thinking about, aggregation and how it is that you can actually handle scale where the number of items grows, you're often going to think about how can you take some existing idiom and extend it. Right, so notice how, of course, color is in use here to show the overplotting. You can't assign some other attribute to color. We're using it. So this is an example where intrinsically, as part of the idiom, we're not only using spatial position, but we're using color for the idiom itself. So it's not available as a channel to show any other thing because we're using it to show the overplotting. Okay, so now let's take a minute to think about aggregation and spatial data a little bit more. So what's interesting and different about spatial data compared to other data? Well, people, cartographers, map makers have been thinking about these issues for a long time. And they've noted some issues, and the big one, MOP, the Modifiable Aerial Unit Problem, uh, that's the acronym for wow, the same phenomenon that we saw in histograms, which was that the bin size really affects the visual shape. Well, this very, very much affects any sort of spatial data. Um, and so specifically, the definition of this is, right, changing the boundaries of cartographic regions, spatial regions and spatial data can yield dramatically different results. And there's really two different phenomena that both can affect you. And so one is what they call zone effects. And that is, um, notice how in this row here, I have three different pictures at first glance, but actually the yellow dots are in the same positions in all three of these views, right? So this is the same data set, and simply deciding, and we're just color coding according to the number of yellow dots in a region. And we see very different phenomena, right? Here we've got things, chopped up into a regular pattern, and it looks like, okay, there's sort of a center here, and then it's dropping off. But notice how if I pick different regions, right, maybe I'm going to pick some irregular regions. This is going to look more like a Voronoi diagram for those of you who have seen these, although not quite exactly one. But so in this irregular shape region, it sort of looks like we have two clusters in the center, not just one, but two. And wait, over here, Now it looks like we don't have any clusters in the center. Now that we've got some different region boundaries, we've got a bunch of regions where these are all sort of much more uniformly split up, and we don't appear to have any sort of concentration in the center at all. So these these zone effects, these different boundaries have given completely different visual indications of what's happening with this data set when we just do what seems like the obvious thing, which is take a region and color code by the density. So there's a lot of trickiness here. And it's not just the zone effects, it's also what's called the scale effects, that the size of the regions that you break things down into really does matter. This is the sort of most similar thing to the histogram problem that we saw before, where the number of bins in the histogram really affects the patterns we see. This is the number of regions that we break it down into really affects the patterns we see. Again, this is the same data set, but just shown at a high level and low level in terms of the number of regions that we have. So this modifiable area unit problem is sort of intrinsic and tricky. And probably you haven't heard of MAP unless you're a cartography geek. And if you are, points for you. But you may well have heard of the instantiation of that, which is completely in the news all the time, every election cycle, which is gerrymandering. So gerrymandering is basically taking advantage of this phenomenon of MAP specifically for political gain, named after a politician from many years ago. And so let's try to understand gerrymandering in terms of this idea of the aerial unit problem. Um, so, here is an example of an actual district in Pennsylvania, which is a completely insane boundary, right? This is not what you might think of if you thought of like a compact region. Um, and this boundary was designed exactly to try to have one party get a lot more vote control than the other. So here's one where um, they try to divide the states up into regions to sort of dilute or magnify the power of one political party versus another. Um, so right, here's this example where if you have a 60% blue-red split with 50 people, how could you divide this up? One could be that you really are, you could stripe one way, you could stripe another way, where you end up with, all 5 blue and none red simply by cutting in the other direction. Notice how you could make some interesting non-compact and non-fair allocations to try to change how one party could win, even though it is in the minority rather than the majority. Um, so there's some nice use of visualization in this Washington Post article from a few years ago that goes deep into illustrating this with a bunch of visualizations. And they showed some examples from real life about some um, ways of making it less or more partisan so you can really affect how one group might win over the other. And then there was actually at least some examples of how some court decisions saying that they wanted to try to take some of that power out and have some more compact and more fair votes really did then change the outcome of elections. So the point I want you to know is not to learn a bunch about US politics, which is not my point here. It's to actually be aware of the fact that there are some fundamental issues underlying this, which makes it non-trivial. You can't just say, oh, I'll algorithmically solve this problem. There is a single right answer. There's certainly some ways of algorithmically having some criteria of things like compactness and fairness, but there's not simply a trivial right answer to pick. And this is why it's so easy for it to get mired into politics. So be aware of the modifiable area unit problem with spatial aggregation in particular. Okay, so now we've been talking mostly about static aggregation with items. Now let's think about how we could do aggregation dynamically. How can we really exploit the use of interaction for aggregation? And the answer to this is going to hinge on clustering. And so let me explain what I mean by that. So first of all, clustering, that just means classifying items into some sort of bins based on some idea of similarity. So you'll need some idea of a similarity measure. This could be like Euclidean distance or Pearson correlation, or we'll talk about some cosine models a bit later. So there's some idea that you can have a similarity metric for items, and then there's going to be some way to partition um, items into some set of bins. In some cases, you pick the number of bins in advance. K means clustering, and then you is one example of that. And then you could divide the data into that number of bins, or you could go the other way around. You could say something a bit more feeling like it's bottom up, where you group together items that are the most similar to each other, and then you just continue this process all the way up. And with these hierarchical algorithms, you don't just get a single set of bins, you actually get a hierarchical structure, a tree that you could traverse where, things at the leaves of the tree are the most, a very fine-grained idea. And so that you can sort of go and with a tree, a hierarchy of clusterings, then you have what we call a hierarchical clustering. And these cluster hierarchies, we can use those with dynamic aggregation idioms. So if we have some idea of, there's a root with completely aggregated information, and then as you traverse down the tree, you can sort of get more and more fine level detail until when you get to the very bottom of the tree, you have the original data set. So that kind of a data structure, which is often derived in order to visualize the data, that's something that we can use in an idiom where we can sort of take into account the idea that these clusters are going to be a lot more homogeneous than like the whole data set would be. And so the key idea is that within the cluster, a kind of statistical measure is going to maybe be more useful and meaningful because of the homogeneity of that cluster. So let's look at a few examples of how to exploit cluster hierarchies in visualization. One of these is a so-called compound graph, and we're going to hear more about networks next time. But what I want you to think about for now is that if you have a node link network, and then you have a cluster hierarchy on top of that network, whether it was derived or maybe interactively chosen by the user, then let's think about how we could visually encode. So here's one where we have connection marks for the sort of base network underneath. And then the hierarchical structure we can show with these containment marks enclosing. And so we can see both the original graph and this hierarchical clustering on top of that original graph all in one. So the original, the combined version. Of course, we could just explicitly think about that cluster hierarchy as a tree diagram, but the interesting part comes when we really try to combine the cluster hierarchy and the base graph in one view. And then we can have some sort of dynamic interaction where you could do something like pick a node and it could collapse or expand out. So you can start actually expanding and contracting these so-called metanodes as you traverse the graph. And so that's one way to use a cluster hierarchy to interactively explore a big complex network. So what's another thing we could do? We could very explicitly show that cluster. Let me actually show you a close-up here. So here's an example where we have, remember we saw a heat map a while ago, where we're just actually, color coding these cells in a matrix according to some attribute value. And in this case, we've got a diverging color map because we're assuming there's some neutral point. We can go up, we can go down. And then we're explicitly showing this dendrogram, this representation of a tree that's showing this hierarchical clustering that goes from the bottom up so that we can actually, for one thing, we can use this clustering to actually decide where to draw these things. So we actually see the boundaries between these clusters more clearly. But the interesting thing that I want you to notice, and this is an interactive system, where by just moving this bar down, you can actually control what level of detail you have of either showing these much smaller cells with the information, or you can actually use the amount of screen real estate you have to show larger areas here. So you can control essentially the granularity of the heat map by just moving this similarity bar up and down. And here we see on the left here a situation where they've moved the bar quite far down to sort of cut off and see only a part of that hierarchical clustering. Here's another example. How could we use hierarchical clustering? So remember with parallel coordinates, we said that the problem was if you have too many of these jagged lines, these polylines that represent items, well, they just start overplotting and it's hard to see anything. So let's think about what we could do in a similar spirit. What if we derive data of a hierarchical clustering of how similar are these points? Remember that the jagged line represents one point in a high dimensional space. So we can say, well, we could aggregate everything together completely if we just look at the root of the hierarchy. Um, Now here we have something, this is actually showing a data set of over 100,000 items. But it's quite understandable here because we're looking at the completely aggregated version. We're looking just at the root of this hierarchical clustering. We have a line going through at this, think of it like a median point, and then we are using this semi-transparent band, this range, to try to show the min and the max values within that cluster. Now, of course, this first one is actually showing the entire data set, but we can move down and we can say, well, show me the top, 6 or 7 clusters, not just the top single cluster. And then what you noticed is that the min-max bands that were very large for the root are now getting split out into smaller regions. And so we can see, here's one up on top here, and there's a clear separation between this cluster versus the rest of them. And so we're able to see more detail, but not an overwhelming amount. And then here we're actually seeing maybe the first, dozen or two clusters, but this is still more precise information than we could see if we just overplotted, 100,000 of these data points. So the hierarchical clustering is allowing us to dynamically choose the aggregation level that we want to see. And so, notice how there's the careful use of transparency so that you have a hope of actually seeing things at once in a way that's more sophisticated than if you just, had these all as, opaque shades of gray, because it would be very hard to see structure that way. And it's colored simply by how close things that are close to each other in the hierarchical clustering are similar colors, and if they're far away, they're different colors, really to try to let you see when there are things that are really different parts of this hierarchical cluster tree. So it's really trying to emphasize similarities and differences here. So these were some examples of how you could use hierarchical clustering for dynamic aggregation idioms. So we've been talking a lot about aggregation for for items, but what does it mean to aggregate attributes? And for that, we need to jump into dimensionality reduction. So dimensionality reduction is the word that's commonly used for what we can think about in this analysis framework as attribute aggregation. And so we're going to use the word dimension a lot because that's what's typically used when talking about these kinds of algorithms. And so the way we can think about it is if we think of attributes as dimensions in some sort of high dimensional space that we can measure, what we want to do is derive a lower dimensional space that captures most of what we care about, that is the variance in the high dimensional space, and minimize the amount of error, that is minimize the amount of information we lose when we compress from the high dimensional space down to the low dimensional space. Now, if you just have, something like, 6 or 7 attributes, maybe you have a hope of really directly encoding all of them. And maybe they're all semantically meaningful and direct and what you want to see. That's the situation we've been thinking about so far. But now let's think about a different case. Let's think about the case where you know you want to, there's something you want to know and you can't just measure it. So you can't, we've talked about a lot of things where you say, oh, well, here's the height of someone and here's the weight and here's how fast they ran the 100-yard dash. And these are all, semantically meaningful attributes that you could analyze and think about. But what about a situation where you can't just measure what you want to know? So let's think about this example from medicine, where let's say that there are things that you can easily measure in a tumor, but you can't measure the thing you really want to know, which is it malignant or benign, right? You might be able to measure some sort of tissue density here. So there might be a lot of things you can measure, and what you conjecture is that by measuring in all these different ways that aren't really quite what you want, um, you're capturing maybe very redundantly something that you do really want to understand. In this case, it's malignant versus benign for the tumor. And so you have this idea that there's a true dimensionality of the data set that's much, much smaller than the dimensionality of what you can easily measure. So those of you who've taken ML classes, you might have heard these talked about as hidden variables or latent factors. Um, and so what I want you to notice is that, here we've got a bunch of dots that are representing this. If you can take, 9 different attributes or things you can directly measure, think of this as a 9-dimensional space, and you're projecting it down to a 2-dimensional space where you're just looking at a scatter plot of these points. Now, here we have color-coded them by a priori knowledge, by some sort of ground truth data where we know that some are malignant and some are benign. And if we didn't have that color coding, we'd still be able to notice that there's really two different looking groups. There's this tight cluster here, which is the benign group, which in this case is color coded blue, but you wouldn't necessarily know that in advance for real data. And then there's this much more spread out um, bunch of the data that is known to, in this case, to be malignant. And so what I want you to notice is that in this 2-dimensional space, we're able to capture the important structure of this high-dimensional data, even though it's projected down to many fewer dimensions. So what this is used for a lot are, for example, to look at documents. So we hadn't talked too much about text so far in this class. And it's notable that, text is a kind of data too. And why isn't text one of the data types that we've talked about? We just focused on tables and network data and spatial data. And in fact, we're still going to talk about network data coming up. Why wasn't text one of those data types? The answer is because typically in a visualization context, what you do is you transform textual data into one of those other forms. And what's very common if you've got a large collection of documents is that we transform that into a really, really, really large table. So let me explain. If you haven't had any kind of natural language processing background, um, the basic idea is that you would take, let's say that you have 40,000 documents, and you you want to treat each document as a bag of words. What do we mean by a bag of words? We mean that we're going to count the number of times that a word appears in a document. Now, of course, this is getting rid of a lot of structure, right? Where that's not like reading text where the order of the words in the document matters. But, we've got 40,000 documents where you don't have time to read them all. What we want to do is try to capture some structure. So what we can do is we can make a table. We can actually check what is, every word that appears in any document anywhere in the collection and say that each one of those words is a column in the table, an attribute, a dimension. And then the rows of this table, the items, are the individual documents. And we could just count the number of times a word appears in a document. Now, of course, a lot of the words will not appear in a particular document, right? Maybe the word kangaroo only appears in a small subset of documents about Australia, and it doesn't appear in any of the others. So it's going to be a very sparse table. Right, think about this table. It's huge. It's got 40,000 words, which are the attributes, the dimensions. It's got 40,000 documents. There's a lot of zeros in there. Now, would we just directly visualize that? No, there's no hope. We can't just directly draw this 40,000 by 40,000 table directly, because 40,000 dimensions is too many to think about. But we could use dimensionality reduction to reduce the number of attributes we show. We could go from 40,000 dimensions down to 2 dimensions. And then we could, in that two-dimensional space, we could draw one point for every one of the original documents. And we would hope that we've captured some of the crucial structure of that, so that documents that have a lot of similar words are actually grouped into visible clusters. And then we could actually go in and maybe inspect some individual documents and try to understand, well, what is this cluster about? And maybe give it a manually generated label. Something like topic modeling could try to automatically create labels, but it turns out that's sort of notoriously tricky and, not very fine-grained and able to be understandable. So it's very common to use something like visualization as part of inspecting these clusters and trying to understand what a meaningful label for them might be. So notice how in the analysis process, this was an example of a chained series of tasks. We first derive the low dimensional table, and then we actually encode that in the form of a scatter plot. And then we interactively might pick an individual dot, really inspect the document that represents, do a little bit of reading, and try to understand whether we can come up with a label or verify that an automatically generated label is actually representative of that cluster. So that's an example of using dimensionality reduction to understand these very large document data sets that create hugely high dimensional tables, but that are very, very sparse and that we couldn't directly look at. So we need to lower the dimensionality. So those of you who've seen this in a machine learning context might think of dimensionality reduction as just something that's done to improve algorithmic performance. To say we've got algorithms that work, just fine with 50 dimensions and they don't work so well with 500 dimensions. So we'll just reduce the dimensionality of the data set using these automatic algorithms and then continue to compute. So this avoiding the curse of dimensionality is a reasonable thing to do. But when we talk about it in a visualization context, we're usually explicitly thinking about looking at the output of after we run dimensionality reduction, then looking at it, typically with some visual interface like a scatter plot, and trying to understand what's going on, right? So in some cases, the tasks that we're doing is we're trying to understand, do these new synthetic dimensions, do they have some sort of semantic meaning? Can we give them names? Can we understand the relationship between the new dimensions and the original ones? Do we actually think that, do we see any cluster structure in this new low dimensional representation? Can we name these clusters? If there's some known class structure that's often, say, color coded, does that match up with the cluster structure that we see in the data? So, here's a few examples. Some of the data sets that people often use for thinking about dimensionality reduction are images, where you actually think of images not so much as an image that a human would look at, but as you can actually think of images as a collection of pixels, where, each pixel has a value, either like a grayscale value or a color value, and you lose the intrinsic structure of what a human would look at with this collection of pixels, and you just treat it as objects in a high dimensional space that then you want to see, is there structure we can capture? So here's an example where running dimensionality reduction has in fact captured it is recaptured without being explicitly told that this very controlled set of images, which is all different shots of the same thing, it's actually come up with one synthetic dimension, which turns out to be the direction you're looking at the face from left to right in terms of the camera pose. And then this other direction was looking up and down. And the key thing to know is that, of course, as a human, you could confirm this, but this was something that was automatically captured by the dimensionality reduction. Um, and it's an example of trying to understand, so this name of this axis, left-right pose and up-down pose, that was not computed automatically. That was something a human made a judgment about. So the synthetic dimensions were computed. And the human looked at a bunch of these data points and tried to understand what is being captured here. Here's another example. Another common data set to use in these is a series of photographs of human written numbers. And the question is, if these are all different ways to write the number 2, are these clustered according to some sort of structure? And again, a human could look at this and say, well, it has to do with how much this top part versus, this bottom, is there a loop on the bottom? You're actually able to see that this scatter plot is capturing that structure, again, in a way that was not mandated by a person, but was automatically found by these dimensionality reduction algorithms. So sometimes what you want to do is not name the dimensions, but understand. You look at these scatter plots and you think, is there cluster structure? Sometimes there is not. Sometimes you really see clear clusters. Sometimes if you've got classes that you color code, they obviously match the clusters, but sometimes they only partially match or they don't match at all. And so these are some of the judgments you might make when looking at dimensionally reduced data. Those of you who've heard of PCA, Principal Components Analysis, this is a very common form of linear dimensionality reduction. It's the simplest and most straightforward one, invented well over 100 years ago. And so it really allows you to try to find structure in terms of axes, right? So if you look at this ellipsoidal, kind of Gaussian distribution looking cloud of points, what you're able to see is, there's a principal axis here that goes this way. We could, here's a second principal axis that goes this other way. And then we're able to actually capture a lot of the structure of this just by saying, well, here's the direction of one axis and here's the direction of the other axis. And here's roughly how long these are. If you have a lot of ellipsoidal blobs, this is actually a very compact way to represent the structure. Of course, if your data doesn't have this kind of distribution, then just like we saw before with some of our other examples, right, of Bach plots, for example, not fully capturing, if you've got data that's not so linear, then it's harder to really capture it fully. So, but this is very good if you do want to understand the relationship between the original dimensions and these new attributes. You can actually get a set of weights that represent how much of each original dimension was used to make these new synthetic axes. So it's very good for that task. Now, what if you don't just have nice linear structure? What if you've got some things that are actually curved? So nonlinear dimensionality reduction can handle that, but it's really hard to map that back to the original dimensions or attributes. So although that's difficult, it can be easier to see the structure. Now, this is something where there's been a lot of work. We're not going to go deep into that in this class. There's papers from all kinds of different areas that go into this in visualization and machine learning and optimization. It actually originally arose out of psychology, back 80 plus years ago. And so some of these techniques you might have heard of, things like TSME, very good for showing cluster structure. There's a lot of difficulties in interpretation. And those of you who are going to use anything like this in your final projects, do have a look at this interactive distill article about some of the challenges in interpreting TSME plots. And I'll also mention for those who haven't seen this, this is a pretty great journal. This is an interactive journal that's using visualization to explore and understand machine learning concepts. So all of the articles are actually have these little mini visualizations embedded all through them, and that allows you to actually, play around with every one of them. So I'm not going to go deep into this particular article here, but just to give you an example of it's explaining a lot about how to actually interpret things like TSNE, and B, that there's an entire journal that uses these interactive visualization-based explainers for communicating a lot of ideas, specifically in this case for machine learning. So those of you who want some inspiration for what kinds of things could you do with these so-called interactive explainers. In fact, there's a meta article about how to use interactive articles to explain things, which would be a great place to have a look. So this is certainly something that's possible for a final project, although you'd want something of much, 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 much smaller scope than one of these full articles, given the amount of time you have. for your final projects. But also, if you want to learn a bit more about machine learning, these articles are pretty fantastic. So back to this. So TSNE is one form of nonlinear dimensionality reduction. MDS, which stands for multidimensional scaling, is another one. It's quite confusing because MDS is actually a blanket word for a lot of different things that is, in fact, both linear and nonlinear. So we're not going to go too deep into it in this class, but just so you're aware of what some of these acronyms are. So, here's an example out of more of these specific articles about trying to give you interactive visualization explainers to understand some of these. And this is really where the optimization world meets visualization, meets machine learning, is this area of reducing the data from high dimensional down to low dimensional space, and what kind of structure is actually correctly captured. Does it capture the cluster structure? Does it over capture cluster and find clusters where they don't necessarily even exist? So again, we're not going to go too deep in this class. I just want to give you some sense that there are many, many algorithmic approaches to this. None of them are perfect. Some are much faster and some are much slower than others. And some are more and less able to capture certain aspects of these high dimensional data sets that have been projected down into a low dimensional space, which we can think of as attribute aggregation. I'll give you one more example of this. How do you do visual data analysis with dimensionality reduction? And it's a fun example because it's out of computer graphics. So in computer graphics, their fundamental goal with what's called reflectance models is to really understand how does light bounce off objects, and you care if you're trying to make realistic pictures of them. So the acronym BRDF, bidirectional reflectance distribution function, is something that you try to use in computer graphics, which really completely captures how light bounces off different kinds of stuff, different kinds of materials. And they actually set up rooms that are, the walls are painted all black and there's a calibrated light source, and you've got a camera that can spin around on a gantry, and you've got the light source that can spin around, and you've got your material sample in the middle to really try to figure out, okay, I'm going to take a zillion pictures and that will give me data about exactly what light does when it bounces off, right? A sphere of marble, a sphere of glass, a sphere of metal. So this all sounds great. What's tricky here, though, is that, okay, so you've got, let's say, 100 different really high resolution images of, light shining off these spheres of different materials. And each one of these pictures is 4 million pixels. And then you're going to try to actually use this huge data set to do a good job of synthesizing a completely new picture of something that's synthetic, like this teapot, which you never really took a picture of, and you're going to try to make it look like these materials that you took the pictures of. But okay, let's think about this from a model point of view. You have 104 materials and 4 million pixels each. So you've got, if you think of each pixel as a dimension in this incredibly high dimensional space, you have 400 million dimensions. So you can't do anything useful with a 400 million dimensional model. You want to have some little like control that says how shiny is it, how greasy is it, how metally is it. You want a small number of meaningful controls, not 400 million sliders, which you'd never get anywhere from. So this is a great use case for dimensionality reduction. And it's also good to understand the difference between the linear and the nonlinear models. So when they used a linear dimensionality reduction approach, like PCA, you can sort of say, okay, so for each dimension that I'm using, I'm going to plot how much error there is. And you can look at the knee in this curve and you can say, oh, okay, it looks like, after you get to about 45 or so dimensions, the error is pretty low. So maybe I'm capturing the structure I care about. And if you try to use that model to make pictures, it's interesting what goes wrong. Here's a picture of, here's this teapot, and here we're actually just focusing on these shiny spots, the specular highlights. And these shiny spots have holes in the middle. Now, if you've ever spent time staring at objects in the real world, the shiny spots, they cannot have holes in the middle. That's not how light works in real life. So this is a model that's not very useful. It's not capturing the real structure of the data set that we want to capture. And if we switch and we use a different kind of dimensionality reduction technique, in this case, they picked a particular one they happened to like because they had been engaged in developing it, called charting. And they plot the amount of error as they add more and more dimensions, how much error is left. Then the error goes down much faster. They only needed like 10 or 15 of these new synthetic attributes, these aggregate attributes to understand it. Um, and the good thing was then when they looked at these scatter plots, it actually made sense. They could notice things like, oh, they could say, well, something that's made out of foam versus something that's made out of metal. They could really start to see a lot more meaningful structure where they could say, okay, make this more foamy or make this more metallic. And so people really went in and, they would look at the pictures and they would try to understand, is there meaningful structure? Can we come up with names for these new synthetic dimensions? And the answer was, yeah, they could. And they were physically realistic and it worked the way they had in mind. And so that was an example where they could say, okay, we can name these axes and then we can just think about moving along in these spaces, and they give us useful control knobs. So the parameters of this model were useful because they used dimensionality reduction to come up with something that really gave them a much more concise controllable space of 10 or 15 dimensions instead of the original 400 million dimensions. So finally, let's take a quick look at the idea of embedding. And so embedding is an approach to visualization where we're really combining filtering and aggregation together, sort of so combined that we can't really separate them out. So within a single view, we're combining information. And so elision or eliding data, well, that's where we selectively filter and aggregate. We could have a superimposition of a lens, as we'll talk about. Um, and if we do that, we can think about, well, what are the design choices? If we're going to have some sort of a focus plus context lens where we're combining contextual information and focus information in a single view, what would that look like? So this is an alternative to multiple views. This is trying to combine things together into one view. And we can think about whether our region is radial or rectilinear. Um, we can think about whether we have one or many regions. We can think about whether the extent of the lens is local or global. So let's take a quick look. So here's an example where we have this is another one of these very large trees. And this is actually the tree of, in this case, it's a a very large tree with an ontology of all kinds of information. Here's the top on the right, and it's actually going from right to left since there's a lot of things in Arabic and Hebrew. And what I want you to notice is some items are dynamically filtered out. We picked world, and then we only expand underneath world. This is for world languages. And all these other possible leaves in the tree, we're just seeing them with these little aggregate triangles. So these aggregate triangles are showing you um, a little bit about what we're not showing, right? So the size of these represents the size of the subtree that was collapsed. So this is an example of aggregation, but this is also an example of filtering. So we've filtered out everything that's not what we've clicked on, and we've got an aggregate representation of the things that are filtered out. And then we do the same thing again. We've clicked on Hebrew, and that's expanded. We've clicked on Arabic. We've clicked on Farsi. So we've clicked on only a few things. So this is an example of this particular idiom is called a DOI tree, a degree of interest tree. So a few things are expanded, most of the things are collapsed, and all the collapsed things are shown with some sort of aggregate representation that just gives you a little hint of the size that would be. Well, what are some other things we could do with this sort of embedding focus and context together in a single view? We can use something like a fisheye lens. So here's something where we have um, a, a very compact heat map view. And then by moving the lens over this, we're able to actually see in enough detail that we can read labels inside, whereas of course there's no hope of reading labels unmagnified. And right here's another example of this radial lens that you're dragging over a scatter plot so you can actually read the labels. So the metaphor here is that you've got a draggable lens. It's a radial round shape. There's only a single lens and it's acting locally. And so let's look at an example of this interactively because it really helps to see this interactively. And so notice how as I'm moving the mouse along, it's as if I just have this little magnifying lens that makes the things under the mouse a bit bigger. And then you could imagine being more able to actually see things like look at the network structure or actually read labels. So that was one that's implemented in D3. There's some other approaches. It doesn't have to be radial. It can be a rectilinear lens. Here's an example of a stretch and squish metaphor where you can actually take this region and stretch it out, and then everything else gets squished. And so this is a different way to see really large trees. We talked about this much earlier back in the first class again, where we compared these two different ways to actually show focus and context, although we didn't use that term at the time. And this again is a tree of, over 100,000 items, but we're able to actually zoom in and see all the way to the leaves in some spots, and then it's highly compressed in others. So this is an example where we could have more than one lens. It's rectilinear instead of radial. So these are both approaches to carefully chosen focus places and then contextual information, but the contextual information has much less detail than the focus. So let's think about the costs and benefits of this approach. A lot of people have spent time thinking about how to combine focus and context information together in a view. And there's some costs and some benefits. So the benefits are that it's all in one view. You don't have to either remember, because remember that we know that just interacting with the single view and navigating around can make it very hard to remember what you've done. And if you have multiple views, of course, there's a limit as to how many of these views you can have. So some people conjectured it might be useful to combine these things together in a single view. Now, you could have a fisheye or even, something more like just a magnifying glass. Now notice how the magnifying glass, you can see things that are distant from it, but, the magnifying glass would actually be a little tiny area of the view here. And then by magnifying, much of what's nearby that is actually completely occluded, so you can't see it. So you have some troubles with occlusion here. With the fisheye lens, we actually see a fair amount of this. We don't completely occlude anything, but it gets highly distorted and compressed as we get towards the edges of this boundary. So these are two different approaches. Now, one tricky thing about distortion is you can't, it actually changes the lengths, right? You're doing spatial distortion. So something like a bar, something where you're deliberately needing to have length coding like a bar chart, it can be quite problematic. That's why they tend to do a lot with networks and trees, because you can still do topological comparisons, as we'll talk more about next time. So, and if you don't know what the original structure is, then just like with cartograms, it can be very difficult to understand the distortion versus the original. So you'd have to be reasonably aware of what the original structure is or have some visual hints to show that. So it might be actually hard to track objects, individual items. So there's been some alternatives proposed. For example, here's a layering approach where instead of using a lens to make certain things larger, you use some sort of a lens to simply change background and foreground transparency so that one specific item is in the foreground and everything else is shown in the background. Here's another interesting one called bring and go, which is an interactive dynamic technique where when you put the mouse over one, instead of just highlighting all the one-hop neighbors like we saw with dynamic layering, it actually brings them all together along vectors from the original direction. So they temporarily come in so you can see them all, and then when you let go, they move back out to their original spots. And again, using this kind of a layering, so you have a hope of seeing them against a complex background. So these are all some different approaches where they've really substituted interaction for spatial positioning, as you would do with these kinds of global distortions. Okay, so we have gotten to the end of aggregation, so filtering and aggregation and embedding.